Welcome back. In this lesson, we're going to look at the measurement of stars. So, how big are stars? How far away are stars? Okay, twinkle, twinkle, little star, how I wonder where you are. That is something that people have always wondered about because we are not leaving Earth. We're stuck on Earth, and so the stars appear to be simply big and small, bright and dim, but some of those dim stars are way bigger than some of the bright stars. If you were to have a candle an inch away from your eye, it would look blazing bright. But if you were to take that same candle and move it several yards away on a dark night, it would look much, much dimmer. So how far away a star is and how big a star is, all combined will give you an idea of the stars. So as we study stars, we need to measure stars. We're measuring their temperature. They're measuring their amount of energy that they're doing. We can make some guesses as to how far away they are. And then all of that together helps us understand stars in general, stars generically. So let's look at some details. All cultures, all people have seen patterns in the stars. A kindergarten kid could look up at the stars and trace patterns. They could see whatever they see. And some configurations in the stars are so obvious that they look like an object that everyone would know, that some of these pictures will be common from one culture into another, but not all the time. And sometimes there would be two or three objects that could similarly look like what the star pattern is, and they would be one in one culture and another in another culture. The patterns that most people learn now, in science especially, are the Greek constellations. So 300 BC, the Greeks had all kinds of stories about the stars, and their constellations was full of their mythology and full of their religion, pictures of the gods and the events of things in their hero stories. And so because Greece was so formative in the Western culture in Western Europe and then later in America, for ages people have studied the old Greek constellations. And there's 88 of them in the northern hemisphere and 88 in the southern. Now some are very prominent and very bright stars with very easy to see shapes. Others are very, very faint with only dim stars in them and that almost no one knows. So in my class, I teach between 30 and 60 northern hemisphere constellations and don't even bother with some of the really, really small, hard to see ones. Inside of some constellations are other patterns that one culture could see and another culture would see something different. For instance, picture here is of what we know in the West as the Big Dipper. So it would be like a drinking gourd or a drinking ladle. The Greeks saw it as part of a larger constellation that they called the Bear, and all the constellations are named in Latin. So the Big Bear is simply Ursa Major, which means Big Bear in Latin. Inside the Big Bear is this very easy to see star pattern that we call the Big Dipper. So a star pattern that is not a constellation is called an asterism. Aster, again, is from Latin meaning star. So it's a star pattern inside, in this case, a bigger constellation that most people would ignore when you see it. The Chinese saw it as a plow. I can see a plow easily here rather than a dipper. So it really depends on what the context of the culture of what people thought they saw based on what they used. I wouldn't see a plow because I almost never plow. I've plowed a couple of times in my whole life, but I don't plow now. And so when I look at it, I don't see what some farmers particular would have seen. Now, the North star is above the two pointer stars in the Big Dipper. So the Big Dipper's front two stars on the right are pointing to the North Star. It's just barely above view. It's right out of the picture, barely above view. And the North Star is in the north, And if you were to draw an imaginary line down to the horizon, that would be true north. That's how you would get to the North Pole. The North Star is the star directly above the North Pole. Okay, so since the Earth is a sphere, we don't see it as straight above our heads. But at the North Pole, that star, the North Star, is directly above your head when you're standing directly at due north. And it's called Polaris for that reason. It's the pole star. The pole star in the North Pole would be directly above your head, and then all the stars would simply circle around it. As the Earth is spinning counterclockwise, the stars would appear to be moving, and they would simply go around and around in circles. Since we are not at the North Pole, the North Star is not directly above our heads, but based upon our latitude. So the latitude where I'm speaking is roughly, I think 38. I believe it's at 38 north latitude, which means that from straight up, I have to go 38 degrees down into the sky in order to find where the North Star is. At 0 degrees, you don't have to move at all. It's directly above your head. At 180 degrees, which would be the equator, or I'm sorry, 90 degrees, which would be the equator, it would be essentially below the horizon because the Earth is so people right at the equator can't see the North Star, and people in the southern hemisphere can't see the North Star. So in the north, any of the stars that are around the North Star that are always in the sky are called circumpolar stars. And at the North Pole, the circumpolar constellations would be a lot of them, but the closer you get to the equator, the fewer circumpolar stars that you'll be able to see all the time in the sky. All the other stars are going to rise in the east and set in the west, just like the sun does. During the year, the sun is actually traveling in the Milky Way, but the Earth is traveling around the sun. So because of that, the Earth appears to have a different sky every few months. So say 10 o'clock at night in the fall, you might see a certain set of stars, and then you go 3 months later and you'll see a different set of stars. You pretty much can see all the stars in 24 hours. Now, when the sun's out, you can't see the stars. So whatever stars are in the sky during the daytime, you simply can't see them. But you're going through the entire sky in 24 hours. So during the entire year, some stars are available, say, at 10 o'clock at night, and at other times of year, they might be available to see at 4 o'clock in the morning or something like that. A cluster of stars are stars that are very, very close together relative to other stars that have been measured. So they're bound to each other gravitationally. So if they're close enough to exert a gravitational pull, now it's not that they're actually moving exactly towards each other, but they're tugging on each other, then that's called a star cluster. Okay? So an open cluster is not as dense. A globular cluster is going to be a dense kind of ball of stars where all of them are close enough to exert a common pull on each other. So there's an open and globular cluster. A binary star system is one in which two stars are in the same, two suns, I guess once you're in a solar system, it's called a sun. Two suns are now rotating around each other. So the common center of mass between those two suns would be like a pivot point, and those two suns are moving around. So imagine two people on ice skates holding hands facing each other and can skate backwards and forwards. They can go in circles. They're not circling. Their pivot point is somewhere in between them. That would be what a binary star system are. And there's numerous binary star systems that have been discovered all over the Milky Way. Doppler effect is when you hear an engine coming to you, say a motorcycle is passing you, and you hear the pitch rise. So it goes from a low sound up to a high sound, and then as it passes you, it drops back down into a low sound. The Doppler effect is essentially that sound is being scrunched by the movement of the motorcycle. So when it's scrunching together, you get tighter vibrations, and it sounds as though it were high. When it's moving away from you, you're getting stretched vibrations, which appears to have a low sound. Well, the same thing can happen in light. So if something is moving towards you, say a star or a galaxy or something like that, it's moving towards you, it's going to scrunch the light waves, and you are going to get bluer. It's going to appear bluer than normal. So the pitch is going to go away from middle up towards the blue end, or at least bluer than it was, towards that side. It's going to be increase in velocity, or increase in frequency. If something's moving away from you, you're going to get a red shift, which is moving towards the red side, or moving with a lower vibrations. And so basically, an astronomer can look at a galaxy and tell whether it's moving towards us or moving away from us, simply based upon the light that it's emitting. If you want to find out where a star is, that is really hard, because we can't move from the Earth. If you were wanting to look at the woods from your window, the woods never change. It would be really difficult to basically determine where every single tree was. How far from your window was every single tree? You could have a big tree that's big because it's close, and it looks bigger because it's closer to you, or you could have a big tree that's simply very far away but very, very large. And so those relative brightnesses of stars are very hard to match, because how do you know without moving from the Earth to know exactly how far they are away? One thing that's pretty close, by the way, these distances are immense. The two distances used in astronomy a lot are the light year, which is equal to the time it takes light to travel in a year. So that's a very big distance, 10 to the 12 kilometers in a year. 10, each zero is times 10 times 10 times 10. So 10 times 10, 12 times would be 1 light year. And a parsec is a little more than 3 times 3 light years. So these are distances that are really, really long. And so when you're studying stellar distances, you need something bigger than miles, because you'd have billions and billions and billions of miles, and that wouldn't be useful. So in order to study where stars happen to be, one useful way is to study them 6 months apart. So look at a star in January, and then look at the same star in July. And when you have that difference of 6 months, the Earth is on one side of the sun in January. It's on the opposite side of the sun. It's as far as the Earth can move. So I can't get off of my porch. I have to stay in the porch. But the whole Earth is moving a little bit from January to July. And so from that distance, it is possible to see a slight difference in the movement of that star and be able to determine its distance. This is called parallax. You do this with your eyes. When you're looking at something, and the reason it looks 3D to you is because your left eye is looking at it from a different spot than your right eye. And so if you can look at it one at a time, that's called parallax, just like astronomers would use parallax. So the apparent magnitude of a star, if I don't know how big a star and how bright a star and how close a star and how far a star is, all I know is that one's big, one's bright, and one's dim. That's all I can tell. So the apparent magnitude is how bright it appears from the Earth. Okay, so when I'm looking at it, one is looking brighter, the other is looking closer. I don't know. Now the sun is not as big as some stars in the galaxy, but the sun is so close that it's so bright that all the other stars disappear when the sun comes out. So that's a case of it being very, very close and looking big. Some stars are big because they're so enormous that they look bigger than other stars, even though they may be farther away. The absolute visual magnitude is basically an apples to apples comparison of stars based upon if they were all placed at exactly 10 parsecs away from the Earth. One would be smaller, one would be brighter, one would be dimmer. So you would have a brightness or a shyness or a magnitude that would be equal if they were all placed exactly the same distance. One star would be big and one would be small, so the big star would be bright and the small star would be dimmer. Now, you have to do a lot of configuration and a lot of math and probably a lot of guessing to know exactly where that would be, because I can't place stars at 10 parsecs. All I'm doing is saying if they were 10 parsecs, I'm going to give them a number that I'm going to call its absolute magnitude. And then from absolute magnitude, I'm comparing all stars together, basically apples to apples. Luminosity is how much energy is dumping out of that star per second. So that luminosity is directly related to how bright that star is, because the energy is what I'm seeing in the light that's coming off that star, or the other electromagnetic radiation that's coming off of that star. So stars are not just bright or dim, but they also have different colors. And the different colors of stars has to do with how hot and cold they are. So if they are very, very cool, then yellow sun is going to go down towards the red end of the rainbow, and you end up having red stars. If they're hotter than our sun, they are tending to go away from yellow into green and into indigo and violet colors, so blue colors. So very, very, very hot stars are going to appear blue in the sky. So there are some stars in the sky that look red, some stars that look orange, some stars that look blue, based upon how hot they are. So that's a temperature. So classifying stars is based upon classifying them by how big they are, how hot they are, and so you can, if you're comparing them each to each other, a great way to do it is by a diagram like this. This is called an HR diagram, an Hertzsprung-Russell diagram. And what they've done is they've taken the absolute magnitude of all stars, or the absolute magnitudes where each star is big or small based upon the same distance from the Earth. And then basically how much energy is being dumped, that's its luminosity, and then how hot it is, what is its color. And if you plot that, you're going to get a plot of all the stars in the sky that we know, and most of them are going to be in this main sequence of stars, this little stripe, diagonal stripe in the middle of the graph. You are going to have some that are very, very hot and very, very dim. These are in the lower left. And you are also going to have ones that are very, very cold, cool stars, but also very, very bright. So bright and cool, those are the ones in the upper right. And all of these different stars in categories can then give us ideas about the differences of stars, and maybe even how a star's lifespan would go. And we'll talk about that later. So main sequence stars, our sun is a main sequence star. So mostly we're going to see that all main sequence stars are burning hydrogen gas. And so they're in their normal life side. And then you have, along the bottom, you're going to have white dwarfs. These are the ones that are very, very hot and very dim. And then you're going to have red giants or supergiants, which are very cool but very, very bright. And so these different types of stars can give us clues about perhaps all stars, and that's for a future lesson.